Welcome! In this session, we'll explore an interesting problem from LeetCode, problem number 646, maximum length of pair chain. This problem challenges us to find the longest chain of pairs based on specific conditions. Let's dive in and break it down step by step. Let's dive into the problem. You are given an array of pairs, where each pair is represented as A_I, B_I, and it satisfies the condition that A_I is less than B_I. The goal is to form a chain of pairs, where one pair can follow another only if the second element of the first pair is less than the first element of the next pair, meaning B must be less than C for the chain to continue. The task is to determine the maximum length of such a chain. The input here is a two-dimensional integer array pairs, where each inner array represents a single pair. The output is a single integer that tells us the maximum length of the chain we can create. Now, let's look at some examples. For the input pairs equals 1, 2, 2, 3, 3, 4, the output is 2. Here's why: the longest chain we can form is 1, 2, 3, 4. Notice that the pair 2, 3 cannot be included in the chain because the second element of 1, 2 is not less than the first element of 2, 3. Therefore, we can only include two pairs in the chain, and the maximum chain length is 2. In another example, if the input is pairs equals 5, 6, 1, 2, 3, 4, the output is 3. In this case, the pairs can be rearranged to 1, 2, 3, 4, 5, 6, where all pairs satisfy the condition that B less than C. This allows us to include all three pairs in the chain, resulting in a maximum chain length of 3. Let's consider another example. If the input is pairs equals 7, 8, 5, 6, 1, 2, 3, 4, the output is 4. By rearranging the pairs, we get 1, 2, 3, 4, 5, 6, 7, 8. In this order, each pair satisfies the condition that the second element of the current pair is less than the first element of the next pair. This means we can use all four pairs to form the chain, leading to a maximum chain length of 4. The key here is that the pairs can be rearranged to find the longest possible sequence, as long as they follow the rule B less than C. Finally, let's review the constraints and edge cases. The number of pairs, n, can range from 1 to 1000. Each pair consists of exactly two integers, A_I and B_I, where A_I is strictly less than B_I, and their values can range from -10,000 to 10,000. Now, for edge cases, if there's only one pair, the chain length is always 1. If all pairs overlap, like in 1, 5, 2, 6, 3, 7, the maximum chain length is also 1 because no pair can follow another. If the pairs are already sorted and non-overlapping, such as 1, 2, 3, 4, 5, 6, the chain length is equal to n. Negative numbers are allowed, and as long as the condition B less than C is met, the chain can be formed. Finally, for large inputs up to the maximum size of 1000 pairs, the solution must be efficient enough to handle sorting and processing within a reasonable time. When tackling the maximum length of pair chain problem, we initially considered a brute force approach. The idea here is to try all possible subsets of pairs and then check whether each subset forms a valid chain. For a valid chain, the second value of one pair must be less than the first value of the next pair. While this method guarantees finding the longest chain, it comes with a significant drawback: the time complexity is n*2 to the power of n. This is because there are 2 to the power of n subsets, and verifying each subset takes n. For larger inputs, such as when n reaches 1000, this approach becomes computationally infeasible. To address this, we moved on to a dynamic programming solution. The DP approach frames the problem as finding the longest increasing subsequence, where pairs are sorted by their first element, and we calculate the longest chain ending at each pair. The transition step involves comparing pairs to decide if they can be chained, updating the DP array accordingly. While this approach is much faster than brute force, with a time complexity of n², it can still be too slow for very large inputs. This highlights the need for an even more efficient strategy. We then turn to a greedy algorithm, which offers a more optimized solution. The core idea is to sort the pairs by their second element and iteratively build the longest chain by selecting pairs that can follow the last chosen pair. By sorting on the second value, we ensure that our choices minimize the current chain's end value, leaving more room for additional pairs. The algorithm begins with a count of 0 and initializes the last selected end value to negative infinity. As we iterate through the sorted pairs, we check if the current pair's start value is greater than the last selected end value. If it is, we include this pair in the chain, increment the count, and update the last end value. This process is efficient because sorting takes O, n log n, and the greedy iteration is O, n, making the overall complexity O, n log n. This efficiency, combined with the simplicity of implementation, makes the greedy approach highly suitable. The key insight is that sorting by the second value naturally optimizes the chain without requiring backtracking or recalculations, as would be necessary in the DP approach. While the dynamic programming approach is versatile and can handle similar longest increasing subsequence problems, it is slower due to its O, n squared, complexity. In contrast, the greedy algorithm is specifically tailored to this problem, making it both faster and easier to implement. By focusing on minimizing the end value of the current chain, the greedy strategy ensures that we leave the maximum room for adding subsequent pairs, which is the optimal choice for this problem. In conclusion, the greedy algorithm is the clear winner here. It strikes the perfect balance between efficiency and simplicity, enabling us to handle large inputs effectively under the given constraints. This makes it the ideal solution for maximizing the length of a pair chain. To solve this problem, we are tasked with finding the maximum length of a chain of pairs such that each pair in the chain satisfies the condition that the end of one pair is smaller than the start of the next. For example, if we have pairs a_x, b_x, and a_y, b_y, we need b_x to be less than a_y for them to form a valid chain. The input is a list of these pairs, and the goal is to determine the length of the longest possible chain. To achieve this efficiently, we use a greedy algorithm. By sorting the pairs based on their end times, we ensure that we are always considering the smallest end time first. This is important because it allows us to maximize the number of non-overlapping pairs in the chain, which is the essence of the greedy approach. The first step in our algorithm is to sort the pairs by their end time, specifically the second element of each pair, in ascending order. This ensures that we prioritize pairs with the smallest possible end time, leaving maximum room for other pairs to be added to the chain. Next, we initialize two variables. The first is current_end, which tracks the end time of the last pair in the chain. We set this to negative infinity initially so that any pair can be added at the start. The second variable is max_chain_length, which keeps track of the length of the longest chain we form. This is initially set to 0. After sorting and initializing our variables, we iterate through the sorted list of pairs. For each pair, we check whether its start time is greater than the current chain's end time. If this condition is met, the pair can be added to the chain. When we add a pair, we update current_end to the end time of the current pair, and increment max_chain_length by 1 to reflect the addition. If the condition is not met, we simply skip the pair, as adding it would violate the chain's validity. Once all pairs have been processed, the value of max_chain_length will represent the length of the longest chain we were able to construct. This algorithm is built on three key insights. First, sorting by the end time of the pairs is crucial because it allows us to always consider the pair that leaves the most room for future pairs in the chain. Second, the greedy choice of adding a pair only when its start time exceeds the current chain's end time ensures that the chain remains valid and optimal. Finally, this approach is much more efficient than brute force, as it avoids exploring all possible combinations of pairs. In terms of data structures, we use a list to store the input pairs and sort them based on their end times. The space used by additional variables, such as current_end and max_chain_length, is constant, making this algorithm space efficient. Analyzing the complexity, the time taken to sort the pairs is O, n log n, where n is the number of pairs. Iterating through the pairs takes O, n, so the overall time complexity is O, n log n. On the space side, we only store the input and use a few additional variables, resulting in a space complexity of O, n. Let's walk through an example with the input pairs 1, 2, 2, 3, 3, 4. After sorting, the pairs remain in the same order since they are already sorted by their end times. We initialize current_end to infinity and max_chain_length to 0. For the first pair, 1, 2, the start time 1 is greater than infinity, so we add it to the chain, update current underscore n to 2, and increment the chain length to 1. The next pair, 2, 3, is skipped because its start time 2 is not greater than the current end time of 2. The last pair, 3, 4, is added to the chain because its start time 3 is greater than the current end time of 2. We update current underscore n to 4 and increment the chain length to 2. The final result is a chain length of 2. The result from the example confirms that the longest chain length is 2. Now consider some edge cases. If the input is empty, there are no pairs to form a chain, so the output is 0. If all pairs overlap, such as 1, 10, 2, 9, 3, 8, only one pair can be chosen, resulting in a chain length of 1. On the other hand, if all pairs are non-overlapping, like 1, 2, 3, 4, 5, 6, we can include all pairs, giving a chain length equal to the number of pairs, which is 3 in this case. These examples demonstrate that the algorithm handles a variety of scenarios efficiently and correctly. The solution to the problem maximum length of pair chain involves finding the longest chain of pairs such that the second value of one pair is less than the first value of the next pair. Let's break the code down step by step. 1. Sorting the pairs. The first step involves sorting the list of pairs based on the second value of each pair. This ensures that pairs are considered in increasing order of their endpoints, which is crucial for identifying the longest chain greedily. The lambda function key equals lambda xx, 1, is used for this sorting. 2. Initialization. Two variables are initialized. Current underscore end is set to negative infinity. This keeps track of the end value of the last added pair in the chain. Chain underscore length starts at 0 and will count the number of pairs in the longest chain. 3. Iterating through pairs. The code then iterates over the sorted list of pairs. For each pair, it checks if the start of the current pair, pair 0, is greater than the current underscore end. If true, this pair can be added to the chain. The chain length is increment, and current underscore end is updated to the end value of the current pair, pair 1. For returning the result, once all pairs have been processed, the function returns chain underscore length, which represents the maximum length of the pair chain. This approach is efficient with a time complexity of O, n log n, due to the sorting step, and the iteration through the pairs is O, n. The overall space complexity is O, 1, since no additional data structures are used. This makes the solution both optimal and elegant for the given problem. This is the complete Java implementation of the maximum length of pair chain problem, mirroring the provided Python solution. The logic involves sorting the pairs by their second element and iterating through them to build the longest chain while maintaining the end of the last valid pair. Key differences include Java's need for explicit type declarations, the use of the arrays.sort method with a custom comparator, and the absence of Python's dynamic typing. The logic remains identical, ensuring correctness and clarity. To solve this problem, we start with an example where the pairs are given as 1, 2, 2, 3, 3, 4. First, we sort these pairs based on their second element. Interestingly, they are already sorted, so the order remains the same, 1, 2, 2, 3, 3, 4. Next, we initialize two variables. Current underscore end is set to negative infinity to track the end of the last pair we added to the chain, and chain underscore length starts at 0 to keep count of the pairs in our chain. Now, we iterate through the pairs. For the first pair, 1, 2, we check if the first element, 1, is greater than current underscore end, which is infinity. This condition is true, so we add the pair to the chain, update current underscore end to 2, and increment chain underscore length to 1. For the second pair, 2, 3, we check if 2 is greater than current underscore end, which is now 2. This condition is false, so we skip this pair. Finally, for the third pair, 3 of 4, we check if 3 is greater than current underscore end, which is still 2. This condition is true, so we add the pair to the chain, update current underscore end to 4, and increment chain underscore length to 2. After iterating through all the pairs, we find that the maximum length of the pair chain for this example is 2. Now, let's look at another example where the pairs are given as 1, 2, 7, 8, 3, 4. Just like before, we begin by sorting the pairs based on their second element. After sorting, the pairs become 1, 2, 3, 4, 7, 8. Once sorted, we initialize the same two variables, current_end is set to -infinity, and chain_length is set to 0. Next, we iterate through the sorted pairs. For the first pair, 1, 2, we check if 1 is greater than current_end, which is infinity. This condition is true, so we add the pair to the chain, update current_end to 2, and increment chain_length to 1. For the second pair, 3 of 4, we check if 3 is greater than current_end, which is now 2. This condition is true, so we add the pair to the chain, update current_end to 4, and increment chain_length to 2. For the third pair, 7, 8, we check if 7 is greater than current_end, which is 4. Once again, this condition is true, so we add the pair to the chain, update current_end to 8, and increment chain_length to 3. After processing all the pairs, we find that the maximum length of the pair chain in this case is 3. Now, let's work through another example with the pairs 5 to 6, 1, 2, 2, 3, 3, 4. We start by sorting these pairs based on their second element. After sorting, the pairs become 1, 2, 2, 3, 3, 4, 5, 6. Following the same approach as before, we initialize current_end to -infinity and chain_length to 0. As we iterate through the pairs, we start with the first pair, 1, 2. We check if 1 is greater than current_end, which is infinity. This condition is true, so we add this pair to the chain, update current_end to 2, and increment chain_length to 1. For the second pair, 2, 3, we check if 2 is greater than current_end, which is now 2. This condition is false, so we skip the pair. For the third pair, 3 of 4, we check if 3 is greater than current_end, which is still 2. This condition is true, so we add the pair to the chain, update current_end to 4, and increment chain_length to 2. Finally, we move to the fourth pair, 5 to 6. For the pair, 5 to 6, we check if 5 is greater than current_end, which is 4. This condition is true, so we add the pair to the chain, update current_end to 6, and increment chain_length to 3. After evaluating all the pairs, the maximum length of the pair chain for this example is 3. By following the same approach, sorting the pairs, initializing variables, and iterating through the list while checking conditions, we can determine the maximum length of the pair chain for any input. To analyze the time complexity of our solution, we start with the sorting operation. The input list of pairs is sorted based on the second element of each pair. Sorting a list of n elements using Python's timsort algorithm takes n log n time, and this is the most computationally intensive part of the algorithm. After sorting, the algorithm iterates through the list once. During each iteration, it performs a constant time comparison and may update the variables current_end and chain_length. Since there are n pairs, this iteration step takes n time. When we combine the sorting step, which is n log n, and the iteration step, which is n, the overall time complexity is determined by the dominant term, n log n. Now, let's examine the space complexity. First, the input list of pairs takes up n space. Next, the sorting operation in Python's timsort algorithm requires auxiliary space, which can take up to n in the worst case. It's worth noting that this auxiliary space usage depends on the implementation and could be optimized to 1 in some environments. Finally, the algorithm itself uses only a constant amount of extra space for variables like current_end and chain_length, which contributes 1 to the space complexity. When we combine these factors, the total space complexity is n for the input storage and sorting, plus 1 for the additional variables. This simplifies to n. Now we can analyze the best, average, and worst cases of the algorithm. In all three cases, the sorting step remains the dominant operation, so the time complexity consistently stays at n log n. This is true regardless of the input structure. The space complexity is also consistent across all cases, remaining n. Additionally, let's compare this optimized solution with a brute force approach. A brute force method would involve generating all possible subsets of pairs, checking each subset to see if it forms a valid chain, and then determining the length of the longest chain. Generating all subsets of n pairs takes 2 to the power of n time, and checking the validity of each subset requires n time. This means the brute force method has a time complexity of n*2 to the power of n, which is exponentially larger than the O, n log n, complexity of the optimized solution. Clearly, the optimized approach is significantly more efficient. To solidify our understanding of the time complexity, let's provide a mathematical proof of the big O notation. The sorting step dominates the overall runtime. Sorting a list of size n using timsort has a well-established worst-case complexity of O, n log n. After sorting, the algorithm iterates through the list, which takes O, n, time. Since O, n, is asymptotically smaller than O, n log n, the overall time complexity is determined by the sorting step, resulting in O, n log n. For space complexity, the input list and the auxiliary space required for sorting contribute O, n. The algorithm itself only uses O, 1, additional space for variables, which does not affect the overall complexity. Therefore, the space complexity remains O, n. When tackling chain-related problems like this, it's important to avoid some common mistakes. First, failing to sort the pairs is a significant error. The order of pairs directly impacts the feasibility of chaining, and sorting, typically by the second element of each pair, ensures the algorithm can identify the optimal sequence. Without sorting, the solution might skip valid chains entirely. Next, we have the issue of incorrectly handling edge cases. For instance, some solutions assume the input is always non-empty or fail to address scenarios where all pairs overlap. These oversights can lead to incorrect results, so robust solutions must account for all possible inputs. Finally, overcomplicating the logic is another frequent pitfall. This could involve using nested loops unnecessarily or manually managing chains instead of leveraging more efficient approaches like dynamic programming or greedy algorithms. Overcomplication not only increases the time complexity, often to O, n squared, or worse, but also makes the code more prone to errors. Another common mistake is confusing the pair ordering. A typical example is misinterpreting the relationship between the end of one pair and the start of the next, such as checking b_i equals c_j instead of the correct condition, b_i c_j. This misunderstanding can fundamentally alter the definition of a valid chain, leading to incorrect outcomes. Additionally, ignoring the optimal substructure of the problem is a critical error. In problems like these, smaller subproblems, like finding the longest chain ending at a given pair, can be solved independently and then combined to form the overall solution. Recognizing this property is key to efficiently applying dynamic programming. Without this insight, solutions often become inefficient and fail to leverage the problem's inherent structure. In interviews, it's crucial to understand and communicate the optimal approaches for solving chain problems. Sorting the pairs first and then applying a greedy algorithm where you iteratively select the next pair with the smallest end value that satisfies the chaining condition is often the most efficient method. For problems requiring more flexibility, dynamic programming is another powerful approach, as it allows you to maximize the chain length by solving subproblems iteratively. Beyond specific methods, you should also recognize common patterns in these types of problems. For instance, if a problem involves intervals, ranges, or chains, it often requires sorting followed by either a greedy or dynamic programming solution. Pay close attention to sorting criteria, especially when chaining depends on the second element of each pair. During interviews, it's important to explain your reasoning for choosing a particular sorting criteria, discuss the trade-offs between greedy and dynamic programming approaches, and demonstrate that your solution handles edge cases effectively. The concepts you've learned in this problem are closely related to other problems on LeetCode. For example, the maximum length of pair chain problem itself is similar to problems like non-overlapping intervals, minimum number of arrows to burst balloons, and video stitching. Each of these problems builds on similar principles of sorting and chaining, making them excellent practice for mastering this topic. One alternative approach for solving chain problems is the greedy method. This involves sorting the pairs by their second element and iteratively selecting the next valid pair to form the chain. The time complexity is O, n log n, due to sorting, followed by O, n, for the iteration. While this method is fast and simple, it's important to remember that it may not work for every variation of chain-related problems. Understanding when greedy methods are applicable is a key skill to develop. Dynamic programming is another powerful approach for solving chain problems. After sorting the pairs, you use a DP array to track the maximum chain length ending at each pair. This approach has a time complexity of O(n) squared due to the nested loops, but optimizations can sometimes reduce this. While it's slower than greedy, dynamic programming is more versatile and can handle more complex variations of chain problems. Finally, there's the brute force approach using backtracking. This involves recursively trying all possible chains and keeping track of the maximum length. While this guarantees correctness, it comes with an exponential time complexity of O(2 to the power of n, making it impractical for large inputs. Understanding these trade-offs, efficiency versus flexibility, is crucial when choosing the right approach for a given problem. Great job! We covered the maximum length of pair chain problem and explored the key strategies to solve it efficiently. Remember to practice similar problems to strengthen your algorithmic thinking. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!